Hello and welcome. This is the AP Physics 1 review for Unit 6, Oscillation and Simple Harmonic Motion. As always, this is a problem review containing both FRQs and MCQs. We'll not cover the content, however, as that can be found on AP Classroom's daily videos. All the problems here will, of course, be in a document linked in the description, as well as this PowerPoint, which contains all the work we've been doing. And with that, let's start with some questions. A mass m is attached to a spring with a spring constant k. The mass is set into simple harmonic motion by a displacement d from its equilibrium position. What would be the speed v of the mass when it returns to the equilibrium position? All right. So it's set in a displacement d, which means that the spring energy, right, the spring potential energy at its maximum displacement, which is d, would be 1/2 k d squared. And if you remember, at its equilibrium position, it's all spring potential energy. There is no kinetic energy. And this is conserved with the equilibrium position, where there is no spring potential energy. It's all kinetic energy. So this will be 1/2 mv squared. Now we can cross out the 1/2 on both sides. We can divide by this m, and then take the square root of both sides to find that v equals d times the square root of k over m. This is answer choice D, so that is our answer. Let's move on. An object swings on the end of a cord as a simple pendulum with period t, and another object oscillates up and down on the end of a vertical spring, also with period t. If the masses of both objects are doubled, what are the new values for the periods? All right. Well, the first thing we can do is write the formulas for the periods of these two things. So t, say p for pendulum, is 2 pi times square root of the length of the pendulum over the gravitational force, gravitational acceleration, so 9.8. And then t spring is 2 pi times the square root of m over k. Well, I think the first thing to be seen here is that if you double the mass of if you double the mass in the pendulum, nothing changes because there is no place to put mass in. So it's just going to be the same period, which is right here. So from that, since this is the only answer choice for the t, we can infer that the answer is going to be B. But just to check, let's move on to the spring as well. If you change this mass into 2m, you're multiplying it by the square root of 2, so you're now going to have t times the square root of 2, which is the same thing as here. So that works. Our answer choice is B. Let's keep going. The graph shown represents the potential energy U as a function of displacement x for an object on the end of a spring moving back and forth with amplitude x0. Which of the following graphs represents the kinetic energy K of the object as a function of the displacement x? Well, the first thing to notice here is that on a spring, the energy is conserved, as in a lot of other places that we're going to talk about. Now, if we draw this line here, right, this is the energy, right? That's the total energy, right? When you add up the kinetic and potential. But the spring energy is only this much, right? It's only all this stuff under here, right? All this stuff under here, which means that all of this stuff in the parabola, above the parabola, below this red line, is going to be the kinetic energy. So at 0, the kinetic energy will be at maximum, at U0. That happens at C and D, not A, not B. But at C, it stays at the maximum potential energy, maximum energy the whole time, which is not true. At the maximum displacement, there is no velocity, kinetic energy is 0, which is what fulfills a D. So D is our answer. C is wrong because on C it does not go to 0 at the maximum displacement points like it should. Let's keep on going. A sphere of mass m1, which is attached to a spring, is displaced downward from its equilibrium position, as shown above, left, and released from rest. A sphere of mass m2, which is suspended from a spring of length L, is displaced to the right, as shown above right, and released from rest so that it swings as a simple pendulum with a small amplitude. Assume that both spheres undergo simple harmonic motion. And they're asking us which of the following is true for both spheres. Well, the maximum kinetic energy is attained as the sphere passes through its equilibrium position. That is true. Right? That is always true for any spring. So that should be true. That should be our answer. Maximum kinetic energy is attained as the sphere reaches its point of release. Well, that's not true over here. Right? The point of release is going to be the maximum displacement. Same here. That's where you're going to have the least amount of kinetic energy because it's going to be all potential energy. So this is not correct. The minimum GPE is attained as the sphere passes its equilibrium position. That's just not true. Right here, at your equilibrium position, you have more GPE with a greater height, which is right here. That's not true. The maximum gravitational GPE is attained when the sphere reaches its point of release. Also not true. Look at the spring over here. If this is the maximum GPE, well, that can't be it because you have more height going to this position. And at E, the maximum total energy is attained only as the sphere passes its equilibrium position. That is, of course, wrong. As we know, energy is conserved throughout the entire period of simple harmonic motion. So there's never be any change of energy, so it'll always be at the maximum energy. All four of those are wrong, and our answer is A. All right, let's keep going on to number 12. Both spheres have the same period of oscillation. Following the expression for the spring constant. Remember back here, we wrote these equations. We can just set them equal to each other and solve. Right, so we can cross out the 2 pi pretty easily. And then we just solve for the spring constant. Square root of Lg equals the square root of m over k over k. Right, we can square both sides, get rid of that, get rid of that. We can multiply by k, right, to get k over g, and then multiply by g to both sides, and get mg. And then divide by L to just end up with k. So mg over L. Now remember, this is the mass, that is the mass of the spring, right? The mass of the spring, as you can see here, is m1. This is m1g over L. That is answer choice D, and we are complete with that one. Move on. A 0.1 kilogram block is attached to an initially unstretched spring of force constant K equals 40 newtons per meter as shown above. The block is released from time t equals 0. So they're asking us the amplitude of the resulting simple harmonic motion of the block. So let's figure out its maximum displacement, right? So at the maximum displacement, what does that mean? So at the maximum displacement, let's call that D. At maximum displacement, the spring force is going to be 1/2 k times d squared. And since k is 40, this is just going to end up being 1/2 times 40, which is 20 d squared. And that's going to equal the amount of kinetic energy. Actually, no, it's not. It's going to equal the amount of gravitational potential energy right here. Right, when it's this far off the ground. And that distance is d. So d times m times g, right, m times g. Right, dmg, mg is, of course, it's 0.1 kilograms times g, that's just going to be d, right, but then we also have our kinetic energy. And our kinetic energy is going to be 1/2 mg squared. Right, so now we can divide by d. Well, really, we should probably figure out how to address this first. Multiply the whole thing by 2, and we end up with 40d squared equals 2d plus mv squared. So now we really just have to figure out what mv is. So we know that m is 0.1. Now I have to think about v. So all right. So how are we going to figure that out? Well, we know that this thing is going to oscillate up and down, and it's going to have this magnitude d, and we want to figure out what v is, right? Now, what we can do is we can take this k equals 40 newtons per meter, right? 40 newtons per meter times 1/2 times displacement squared, and set that equal to 1/2 mv squared, right? Now, this works not only when you're going down, right, when you have to add this 2d, but even when you have to subtract d. And now, why would you have to subtract d? You have to subtract d when this goes back up to here, right? Because it's simple harmonic motion, right? It's going to go down and then back up, right? So this is its natural, this equilibrium position. It's going to go down to maximum displacement, and then it's going to come back up, and then it's going to go back up again to its equilibrium position. And if we solve this, right, we figure out what? Figure out that v squared equals that 0.1 v squared equals, why am I blinking right now? I don't know. Equals negative, we figure out that when we plug this in here and we solve for d, we get that d is 1/40 meters. And that is that question. All right, let's keep going. Let's use the same principles on the next question. Right, the resulting period of oscillation, that's what we're asked for now. And the resulting period of oscillation, well, we have this spring, right? And that's going to be, let's see, 2 pi times m over k. M over k, well, m is 0.1, k is 40. M over k is going to be 1/400. Square of that is 1/20. That's going to be 2 pi over 20, which is pi over 10 seconds. The answer is C. Let's keep going. Let's see. Now we have some graphs, right? Graphs are an important part of this unit because we have, of course, amplitude, the period. We have lots of things that are asked in these. So which of the following graphs shows the kinetic energy k of the particle as a function of time t for one cycle of motion? Well, what we know is that at the minimum displacement, right, we have at equilibrium position, so no displacement, we have maximum kinetic energy k. So right here, we have no displacement. Right here, we have no displacement. Right here, we have no displacement. In these graphs, all three of those should be at the maximum. The only graph that does that is B, right? You have the peak there, the peak there, the peak there. This one does not have a peak here in A. This one completely messes it up, puts the peaks in the wrong spot. And this one only has one here, right? And then, of course, if we wanted to check it, we could see that at the maximum displacement, there's no kinetic energy, right? As you can see, there's no kinetic energy here. Here, that fulfills all the conditions, and our answer is B. Let's move on. All right. A block on a horizontal frictionless plane is attached to a spring as shown above. The block oscillates along the x-axis with simple harmonic motion of amplitude A. So the following statements about the block is correct. Well, before we even look at the answer choices, we know two things about the block. We know that at the amplitude, the maximum displacement, there is no velocity, there is the maximum spring potential energy. And we know that at the equilibrium position, the kinetic energy is the maximum and there's no spring potential energy. So, what can we do with that? We can immediately see answer choice C is incorrect, right? That's just not right. At x equals A, acceleration is 0. Also not correct, because if there's a net force, there's an acceleration. There is a net force because you have a displacement from the center to the equilibrium, and you have a spring constant. So that's incorrect. X equals 0. And then it says here, x equals 0, acceleration is at a maximum. Well, that's not true, is it? Because, first of all, it's decelerating, right? It's losing velocity, right? Second off, well, it's at x equals 0, so you have no displacement, so you have no really net force. So you don't have an acceleration at all, at least not a positive acceleration. The answer choice is B. Of course, that is correct. The amplitude A is the highest point it reaches, or the lowest point it reaches, conversely. So x equals A, maximum displacement. Let's get on to 22. This is the same thing we just said. At x equals 0, potential energy is at a minimum. So this one could be correct. At x equals A, potential energy is the maximum. Not correct here. At x equals 0, the kinetic energy is at a maximum. It's equilibrium position, so that's incorrect. And at x equals A, kinetic energy is at a minimum because there's no kinetic energy. So that's incorrect. And the answer is A. Let's move on. A simple pendulum consists of a 1 kilogram brass bob on a string about 1 meter long, has a period of 2 seconds, and they're saying the pendulum has a period of 1 second. If what? Well, what can we do? We can write out the formulas for period, or formula, singular, for the period of a pendulum, and it would be this. Now, of course, you cannot change the gravitational force or gravitational acceleration on Earth because that doesn't work. And if you look at this, there's no place for mass. So mass is not going to matter here. We can change the length, though. So if we change the length to one with 2 meters long, right, then this would become 2L. And that would multiply this by 2. And that would make the period double. If you replace by one about 0.25 meters long, 0.25 meters, then it would make it 1/2. And that would be incorrect because you're trying to make it double. The answer is B. Let's keep going. A pendulum with a period of 1 second on Earth. Acceleration due to gravity is G. Taken to another planet where its period is 2 seconds. The acceleration due to gravity on the other planet is most nearly what? Well, the period is this, and apparently that equals 1 second. Right now, if we want this to equal 2 seconds, then since this is staying the same, we're doubling this, so we should quadruple this. And since we're changing the gravitational force, if this has to be quadrupled, then the gravitational force has to be divided by 4. So it would be G over 4. Answer choice A. Let's keep going. This is our last multiple choice question, and it is: an ideal massless spring is fixed to a wall at one end as shown above. A block of mass m attached to the other end of the spring oscillates with amplitude A on a frictionless horizontal surface the maximum speed of the block as Vm. They're asking us for the force constant of the spring. Well, we can again use our equation that 1/2 k x squared, or a squared because they're giving it to us, is going to equal 1/2 m times Vm squared, which is our maximum velocity. Right, cross out the 1/2 on both sides, and they want us to figure out the force constant. So we divide by a squared on both sides, and we get that the force constant equals mass times the velocity squared over the amplitude squared. Looking at our answer choice, that is answer choice D. We are done with the MCQ review. Let's move on to 2 of our FRQs. Alright, let's get to the first one. A block of mass M is resting on a horizontal frictionless table and is attached as shown above to a relaxed spring of spring constant K. A second block of mass 2m and initial speed v0 collides with and sticks to the first block. Develop expressions for the following quantities in terms of m, k, and v0. So they're asking us for v, the speed of the blocks immediately after impact. Well, onto another slide. We have more space to work. This is a momentum problem, isn't it? You have you have a mass and you have initial velocity. It's sticking, inelastic collision, asking us for a final mass. Well, we have 2m v0 going in that direction over 3m, right? So then that means that our velocity would be 2/3 v0. Keep going, part B. The maximum distance the spring is compressed. All right, we have an initial velocity, we have a spring constant, we have a mass. We plug in to the same equation we used up here, right? The Ka squared equals mvm squared, and we get that Okay, I just removed the 1/2 from both sides prematurely because we really don't need it. Kx squared equals 2/3 v0 squared times m. Dividing by k and square rooting, we get that x equals 2/3 v0 and square root of m over k. Right, recall that this is because m and k each have one factor each, but we squared this velocity. Right, last one, at least in this question. C is trying to find the period of the subsequent simple harmonic motion. Well, let's see, we have, that's just going to be 2 pi times m over k. But what is our mass? Our mass is 3m. So instead of just putting m there, we have to put 3m. That uses the variables they're asking for, mk and v0. And that is it for that FRQ. Let's move on. All right, next FRQ. This is the last one. A simple pendulum consists of a bob of mass 1.8 kilograms attached to a string of length 2.3 meters. The pendulum is held at an angle of 30 degrees from the vertical by a light horizontal string attached to a wall as shown above. And they're asking us to draw a free body diagram showing and labeling the forces on the bob in the position shown above. Well, first off, we have a force of gravity, right? F, G. And then we have a force of tension exerted by that string. Force of tension. And then we have this other tension, right? This other force of tension here that's pointing like that, right? And it counteracts, right? One important thing to note is that the block isn't moving or accelerating. So all these have to cancel out, and this Ft cancels out the other two, force of tension, and that is the free body diagram there for part A. All right, let's go on to part B. Calculate the tension in the horizontal string. Well, what do we have here? So, we could just plug in to like all this free body diagram stuff that we did, right? We can find the tension, and we can find the tension of this other string and the gravity. But is there a better way to do it? Let's see. We have an angle. They've given us the angle, and does not look like there's a better way. All right, so let's just plug and chug. All right, 1.8 times g. Right, that is the force of gravity. Right, which is also, if you draw these components, like now be sure, right, on the actual AB exam, you don't draw the components in this diagram, in this free body diagram, because on the when they ask you to draw a free body diagram, no components. You can draw an extra one that has it, but not on this one. So this is going to be 1.8 g, and the 30-degree side is right here, which means that this side right here that has the tension force is going to be tangent of 30 times 1.8 g. Now tangent of 30 times 1.8 is going to be 1.04 g. So that is, whoops, that's the wrong one. This one. That is going to be the tension force, 1.04 g. 1.04 times 9.8 is going to end up being 10.18 newtons, and that is part B. Keep going. All right, C, the horizontal string is now cut close to the bob, and the pendulum swings down. Calculate the speed of the bob at its lowest position. All right, now this is another one of those problems, right? We want to find the speed at its equilibrium position, and what we have, we can figure out the force of the gravitational force and the force of the pendulum itself, right? So right here, what do we have? So when we let go, when we cut this string, right? Right before we cut the string, right? This has only gravitational potential energy. It has gravitational potential energy of how much? Well, what's the height? Well, the height, the string, right? The string is 2.3 meters, right? So from here to here, that's 2.3 meters. And we want to figure out how much this is. Well, using this 30 degrees, we know that this part is going to be cosine 30 times 2.3. Cosine 30 times 2.3 is 1.99. So 2.3 minus that 1.99 is going to give us 0.31. So that height is going to be 0.31 meters. And of course we have, that's our height. So now we have mass, 1.8 kilograms, and then the force of gravity, acceleration due to gravity, 9.8. And we multiply all of those together, and we get 5.44. 5.44. And that is the amount of energy that this has. Now this is equal to hold up, why the marker is not working. Is equal to 1/2 mv². squared. Multiplying by 2, dividing by the mass, and square rooting gives us our velocity of 2.46 meters per second, and that is the speed at the lowest point, the equilibrium point of the bob. Let's move on to part D. They're asking us, how long will it take the bob to reach the lowest position for the first time? Well, remember what the period means. Right? The period means that you are starting at a position and you're going to the equilibrium position. You're going all the way to the other side. You're coming back, and then you're going back to the beginning. Right? So that's like that's going to be 4 times the amount of time it takes to get to the equilibrium position the first time. So if we found the period and then divided by 4, that would be our answer. Well, the period divided by 4 is just going to be 1/2 pi times the square root of the length over gravity, and we plug that into the values we know into the equation. Right, the length is 2.3, gravity is 9.8. Take the square root of that, multiply by pi, divide by 2, and we get 0.761 seconds, and we are done with that FRQ. And that is it for Unit 6, Oscillation and Simple Harmonic Motion. I hope you enjoyed it. I hope you found it informative. I'll be back soon with the next and last unit of AP Physics 1, Torque and Rotational Motion. I'll see you then.